Okay, in this segment, we're going to talk about how we discover pharmacogenomic associations. Discovery of PGX associations. And please note, I'm using the word association. That could be purely statistical, and there is always work to be done to identify the causal variation. But let's at least find the associations first. In general, you can think about two broad approaches. One would be called genotype to phenotype. And the other would be called phenotype to genotype. So let me just give you the general idea for each of these methods. So in the genotype to phenotype, so this is 1, this is 2, now we're talking about 1. You pick a gene that you believe to be important for drug response. Pick a gene important for drugs. How you do that requires you to be smart, clever, understand pharmacology, understand a little bit about how drugs are either metabolized or how they work. You measure variation in that gene. You sequence it a bunch. Sequence it. Here's a lot of individuals, and I'm looking for where they have variants. Either common, there's a common one, or rare. So you measure the variation in the gene, and then you seek patients with unusual drug response with those variations. So let me just take you through that. So you do a bunch of sequencing and you find a variation that's interesting. This is patient 2. And you say, okay, patient 2 had this really interesting variation. I've never seen it before. Does patient 2 have an odd drug response of any kind? So I found the genotypic change, and I'm now looking for the phenotype. And you might say, oh, look, this patient did indeed have an unusual response to drug X. That allows me to associate this variation with the response to drug X. So it's the pros are that you know that there exists variation in the gene. The con is that you have to look for the phenotype. I'm going to use phi for phenotype in this lecture, in this segment. You have to look for the phenotype, and it's not clear that you'll find anything. But this is a common way to search for pharmacogenomics associations. The second way, I'll try to fit it in here, is the phenotype to genotype. Look for clinical variation in drug response. Clinical variation in drug response. So now you've solved the problem that genotype to phenotype has of knowing what the phenotype is, because you're looking for a population of people, you give them all the same drug, and you see variability. Great. Could there be an underlying genetic cause for that variability? I should say that you can have variable drug response because of genetics, but you can also have variable drug response because the patient hasn't taken the drug, or because the patient has food in their stomach that is blocking absorption of the drug. So there are many sources of variability, but you would like to know if there's a genetics source for this clinical variability. So when you find the clinical variability, you now look for genes, look for genetic variation that correlates with this clinical variation. It's kind of the opposite problem. The pro is that you have clear phenotypic variability, whereas here you had clear genetic variability. The con is you're not sure which genes to look for. So I'm just going to say question mark, which genes. For many years, clever pharmacogenetic scientists either did genotype to phenotype or phenotype to genotype based on their knowledge of clinical variability, the PK and PD pathways that were known or partially known for the drugs to generate hypotheses about either which genes would be important or which phenotypes would be worth measuring. The world kind of changed about 15 years ago when we became capable of doing genome-wide association studies. Genome-wide association studies allowed us to have a systematic way to do phenotype to genotype. The key idea was that SNP chips allow us to measure 1 million SNPs throughout the genome. So we don't have to have a strong hypothesis about which genes are responsible for the phenotype. If we have a good phenotype, and if there is a genetic influence on that phenotype, then a SNP chip allows us to interrogate all genes at the same time to see which of them might be involved in that phenotype. So let's go through how a genome-wide association study works. Genome-wide association study. So the first key element for a GWAS are these SNP chips. And we've talked about them a little bit in previous segments. They measure 1 million SNPs. The SNPs are spaced evenly. We've talked about that. About 1 every 3,000 base pairs. And they tend to be common variants. And always SNPs on SNP chips by definition. Okay. We also need a large number of patients with a clinical phenotype of interest. Clinical phenotype. And we need a large number of patients without that clinical phenotype. This means without, that means with. Sans and cum, for those of you who are Latin fans. Okay, now let me just say parenthetically that this is for a yes-no situation. So I had a terrible response to the drug, or I had an okay response. It's also possible to do GWAS for quantitative traits, where instead of yes-no, so this is binary, 1, 0. Quantitative traits have a value from, say, 0 to something. I'll call it big R. And these ideas extend to quantitative traits, but I'm going to discuss this in the context of binary traits because it's a little bit easier. So now, a GWAS is really a beautifully simple idea. And here's how it works. You are going to measure 1 million SNPs on all the patients. We're going to call these cases. And we're going to call these guys controls. And let's just take one SNP. We have SNP number 72, I'm making this up, which is a GT SNP. Okay. We're going to do this 1 million times. This is one time. We're going to have the cases. We're going to have the controls. We're going to see 3 different genotypes in this population. There'll be people who are GG. There'll be people who are GT. And there are people who are TT. So we can make a little table. Where we count up the percent of cases that have GG, GT, and TT, and the percent of controls. Well, the most common case will be that this SNP has absolutely nothing to do with the genetics of the drug response, and therefore cases and controls will be indistinguishable based on this SNP, which means you might have 10% GG, 30% GT, and 60% TT in the cases. And then, there's going to be a little bit of statistical noise. So maybe this will be 9%, and this will be 31%, and this will be 60%. But when you do statistical tests, you say there is no difference between the frequency of the different genotypes at this SNP location 72, cases and controls, SNP 72 has nothing to do with this clinical phenotype of interest. It is not useful in predicting 1 or 0. But let's think of a more interesting case. Let's do a little erasure. And now let's imagine a genetic variant that is actually, so now this is SNP, I got to change the number because this one is going to be a good one. So this is SNP 4023, and it's a GT SNP as well because I don't want to redraw this part of the table. So it's a GT SNP. And now we see this. For GG, we see 20%. For GT, we see 35%. And for TT, we see 45%. Whereas for the controls, we see 5%, 15%, 80%. We're not going to discuss the statistics. I can tell you, for those of you who are statisticians, that we use something called the chi-squared test. If that means anything to you, that might make sense. If not, don't worry about it. But what we're going to do is we're going to ask, given the number of cases and controls that we have, and we acknowledge that there's going to be a little bit of variability, but is that variability such that the difference between 20 and 5 is expected to be possible or extremely unlikely, and therefore due to the fact that the GG really does have something to do with increasing the risk of this clinical phenotype? We do that through the statistical chi-squared test. There are other tests as well. And we say, wait a minute, SNP 4023, the GT SNP, seems to be associated with our phenotype of interest. And that is worth a couple of exclamation points. Now, I told you we're doing 1 million of these tests. So how do we look at these overall? And it's done with something called a Manhattan plot. And a Manhattan plot looks like this. You have all the SNPs lined up along the x-axis, sorted by chromosome position. So here we have chromosome 1, chromosome 2, chromosome 3, 4, ... 21, and then maybe even X and Y. And so there's literally well, not zillions. There's many millions of SNPs on each of these chromosomes. And then what we plot here is negative log of the p-value of the chi-squared test. So I didn't talk about this, but the chi-squared test will give you a p-value, which is the probability that the null hypothesis, which is that there's no difference between these, the probability that the null hypothesis cannot be rejected. So if I have a p-value of 0.05, that means there's a 95% probability that you can reject the null hypothesis and that these truly are different. But there's a 5% probability that they're not different, and it's just within normal noise. So a p-value of 0.05 is pretty confident. A p-value of 0.0001 is much more confident, because that means there's only a less than 1% chance that the null hypothesis is true. And it's by far more likely that these numbers are truly different. So you plot the negative log of the negative log base 10 of the p-value. And so you get these nice things like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, where, just to be clear, 1, 2, 3, 4, 5, 6 means the p-value was 10 to the negative 6th, because the log base 10 is negative 6, and then negative 6 is positive 6, which is here. So what you do is you take the p-value for every SNP and you plot it. Most SNPs cannot reject the p-value, cannot reject the null hypothesis, and then have a very low p-value. And that's one of the ones that I'm drawing here. But every now and then you will get a SNP or two that have a high p-value. And so it'll be a spike. And then it'll go back down, and then there'll be another spike, and maybe one more spike throughout the whole genome. okay? You usually have a cutoff. I'm not going to go into the statistics, but there's usually a cutoff of the minimum level of significance that you're interested in. So this is our cutoff for rejecting the null hypothesis, and that gives us 3 hits. So these are 3 SNPs that score the highest locally for the significance, and since they're above the cutoff, we really believe are associated with the clinical phenotype of interest. A couple of things to say. One thing to say is, I drew several dots here, not just one dot. That's because of LD. Because of LD and the correlation of SNPs, there'll be the best SNP, and then the SNPs around it, because they're correlated, will also show some correlation to the clinical phenotype. Because correlation is transitive. If A is correlated with B, and B is correlated with C, then there's a chance that A will be weakly, but still correlated with C. And that's why you see several dots here getting, and the reason it falls off is because as you get farther, the LD erodes, and you see less of a correlation. So these are your 3 hits. So what do you do now? Well, you do a super duper close-up of this region of the genome. So now I'm going to explode this region. So I'm looking here, where this is this little segment there. I'm exploding it. And for example, I want to know where are the genes. There's maybe a gene here, maybe a gene here, maybe there's a gene here. Our SNP might be right there. That might be our big red SNP that I highlighted with the great p-value. Does that mean that this is the causal variant? No. It means that it is the highest correlated to the trait, and in LD with lots of other variants that may be the causal variant. For example, if there is a nearby SNP over here or over here in the protein coding region, it may be the causal variant. Or over here in a control region. There's the same thing with this gene. So you look at these genes, you say, what is their function? Do I know anything about this gene? Does it make any sense for this gene to be involved in the response to that drug? Well, if this is a cytochrome or a transporter, or if this is a G protein coupled receptor that is known to bind to small molecules, then you get excited and you say, oh, this is the tag SNP. These are the SNPs that might be the causal SNPs. But here you have to do biology. You have to get together with your favorite experimental team, and you have to say, how are we going to dissect this to figure out what the causal variant is based on our GWAS hit? But don't be disappointed. You've spent a lot of money to get this data, but you are now very focused in your search. You started out having no idea where in the genome. I'm going all the way to the other side of the board. You had this clinical variability, but you had no idea what genes to look at. You did this GWAS. You went to every piece of the genome looking for an association. You found 3 regions worth studying. And then you looked, and you now are focusing in a very focused way on 2 or 3 genes in each of these regions, or 5 or 10, but it's way less than 25,000. And that's been the success of genome-wide association study in pharmacogenomics. They also do this for disease, where the clinical phenotype is disease. It turns out that for complex diseases, it's a very tricky story. You don't always get hits, and sometimes the hits are there, but they're not significant. So if I had a peak here, well, it sure looks exciting, but if I really believe my cutoff, then this is not a significant hit. For disease genetics, GWAS has been a plus-minus story. For pharmacogenomics, because many of the effects of the pharmacogenomics, many of the genes have strong effects and are easy to identify or easier to identify, it's been relatively more successful. The big problem for pharmacogenomics has been getting numbers of patients. So if you have a rare side effect that you're trying to understand, there may be only 300 people in the world who've ever had that side effect. So your chances of getting 1,000 examples is 0. So the big problem with GWAS for pharmacogenomics is not the idea of doing the GWAS, but the availability of cases, not so much controls. We can get the negatives, but the positive cases. So very often, pharmacogenomics GWAS are underpowered. And underpowered is a technical, statistical meaning of you don't have enough patients to see a clear signal. If you're not underpowered, they tend to find causal variance. Not directly, but after you search around the SNP to look for the hits that are there, the genes that are likely relevant, and you do a little bit of extra work. So that's a summary of the discovery of pharmacogenomics associations through the primary means of discovery, which has been genome-wide association studies with common variant SNP chips. The future holds sequencing, where we give up on common variants and go and look at rare variants. And that'll be the subject for a different segment.